Um, cool. So that's the welcome, and then I'm going to attempt to give an overview of this cloud native geospatial um, world. So I want to thank everyone who's new to this world. We tried to welcome a lot more in, and I hope my explanations make sense. And yeah, for the purpose of this talk, so I wear a lot of different hats. I do product strategy at Planet. I'm a technical fellow at Radiant Earth. I'm on the board on the OGC, and this talk is given for sort of all these hats and none of these hats. They all support my time on this, but I'm not speaking for an organization. I'm really trying to speak for this community. So the goal is to take us through the basics. What is cloud geospatial and why does it matter? And then we'll survey the state of the ecosystem and close with just a couple of thoughts on the future. So let's start by getting on the same page with what is cloud native geospatial. The simplest answer is fairly self-evident from the name. It's geospatial that assumes you're running on the cloud. But the whole ecosystem really starts from a deeper question, and that's what if geospatial tools and software were actually built from the ground up for the cloud? You know, if you never had to download data to a desktop tool to do GIS for remote sensing, how would the workflows look different? How would the tools look different? And this group of people presenting today has been collaborating to really answer that question, as you're going to see in a wide variety of talks. So there's two standards at the center of the ecosystem, and then a lot of interesting innovation at the edges. Cloud optimized GeoTIFF emerged as the core format to store data in, and then STAC, spatial temporal asset catalogs, pairs beautifully with COGS to complement it with additional JSON metadata, and it also works with a variety of other cloud native geo formats, as well as with legacy formats that need to be downloaded. So we'll dive a bit more into each. First is cloud optimized GeoTIFFs, and it's a special form of one of the most classic file formats of remote sensing, the GeoTIFF. But it's been specially formatted to work on the cloud to allow web clients to request exactly the piece that they want. For a quick tour of COG in action, let's check out this one I put up on Google Cloud. So note this is 3.7 gigabytes. So on a nice, fast fiber Wi-Fi connection, that's maybe 10 minutes to download, you know, potentially hours or even longer on a slower connection. So one thing here is you have to wait before you can even view it. You have to get it on your computer to then open in some sort of software that understands a GeoTIFF. But if it's a COG, you can view it right away. This shows a site that lets you load any URL with a COG into WebTile so you can share it with others. So you just take that URL, drop it in here, and boom, you instantly see it. And it's the full resolution data. You can zoom in as far as that data goes. It's not just a browse product or overview. And this is backed by a scalable Lambda tiler run by Radiant Earth. Anyone can try this out. It's also really easy to install your own, and there's a whole set of these. And the cool thing about them is how scalable they are. It takes that scalability of serverless Lambda, applies it to tile services. And it's really cool to see how just easy that is to scale up to millions of people. 10, 15 years ago, being involved in mapping, it was a whole lot of work to set up your servers, to be able to auto scale up. And now it's just kind of deployed to Amazon or Google Cloud Functions or Microsoft. So this particular COG was made in Google Earth Engine. You can produce COGs from any operation you can imagine. This one was a clip and composite of a whole bunch of planet imagery. And there's a whole number of tools that support COGs now. So it's not just kind of source satellite imagery, but also do your own operations and publish that as a COG. This is the mosaic that is produced. And this one's rendered as false color on the fly by the tiles.radiant.io preview. So false color means we're visualizing that fourth near infrared band. So it's non-visible information. It's taking vegetation health and pulling that out as red. And we can do that because the COG stores all the raw data. It's not just a particular web visualization that's been made up front. Like I said, it renders that on the fly. And then these cloud optimized geotiffs can also be used in a desktop GIS. So again, I take that same URL and actually I just realized this is an older QGIS one, newer QGIS ones have it fully native. You just drop in the URL and it works. And it just demonstrates how data can be streamed. You don't have to wait 10 minutes or more for it to download. Since it's accessing the full bit depth data and full band data, you can even do analysis in QGIS streaming right away. And ArcGIS Pro, if you lean that direction for desktop GIS, also has full support for reading and writing cogs. And then one of the coolest advances by the EAX team is a pure JavaScript cog reader. They're going to share more about this in their lightning talk, but there's this whole serverless trend, and I almost see this as less servers than serverless. It's just a cog on Google Cloud, and it's read directly with JavaScript. There's not even a Lambda tile server in between. And again, you can do client-side analysis, you can do band manipulations, and you'll see a couple talks on people doing really cool stuff with cogs in the browser. And then Azavia has built the ability to import any cog online into Raster Foundry. Exact same file for all these visualizations. They have a whole bunch of analysis tools. I didn't manage to get it into this little video, but anything that's possible in Raster Foundry, you can do on the cog, on the fly. And then you can also start to use the labeling tools to annotate imagery. So the other core standard in this emerging ecosystem is STAC, Spatial Temporal Asset Catalogs. This came about from a bunch of people gathering to try to solve an annoying problem in the Earth imagery space. You have lots of different sites that you need to go to be sure that you have all available imagery for the area. And the situation is just as bad for APIs. Every single one of those visualizations is powered by a slightly different API. They're all JSON RESTful, but each has a different way of organizing. One might do min and max for cloud cover. One might do clouds between 0 and 1, another from 0 to 100. So STAC really aimed for this common language for searching for imagery, but we realized that it shouldn't just be imagery. It should be any geospatial asset. So any type of data that you might download to further analyze, we want to be able to catalog. But we took a different approach than what had come before. We really focus on the smallest, easiest building block that can enable others to innovate. We're not trying to stand up an index. We're just trying to make data indexable. So the core is a small JSON file, and that can be shared either statically, just place the file on S3 or Google or Azure, or it can be through a dynamic API. So if you already have a service up and running, you can easily sort of add STAC on top of that, and you'll see a number of people talking about both approaches today. And with this core, every record that is online can be represented as a web page. So this enables people to refer to a single location online for any geospatial asset. It's kind of challenging to share data now. You have to send in these big files. With this, a JavaScript tool turns a STAC from that JSON file to these interactive pages. And then you can see this zooming in on the web tiles. If it happens to be a cloud optimized geotiff, the image is browsable and shareable in the same location that it's found. And eventually we'll work to have more cloud formats. I think you'll hear about Entwine and point clouds later. You can see a point cloud viewer as well with STAC. So STAC and cog are really complementary pieces of technology. But the thing is, it sort of gives you what you used to need a desktop GIS for, to look at large scale imagery. With this, you can go full screen, you can share what you're looking at, you can get a quick visualization of what's happening without even having to download it. And I really want to emphasize the sort of radical simplicity of these two technologies. They make data available and accessible, but they do the simplest possible thing. And that's so other tech can grow and adapt. And we're starting to see much more of that. Okay, so those are some cool demos. Things look neat on the web, but does this actually solve anything? So there's a few different areas I believe Cloud Native Geospatial has a role to play. I'll likely do some blog posts on these topics. I actually got a bit behind on working on this talk since I had to do a whole bunch of organizing to pull this together. So I don't know if these arguments are as tight as they could be, but I wanted to at least attempt to answer the question of why. So first up is global analysis. As we face global problems, we need dashboards like this one from Global Forest Watch. And the key is it's both the global trend, you can see the forest loss by year for the globe, but it's also a detailed analysis for each country and even state. This global scale of analysis is essential as we tackle global problems. We can't just do analysis of a single area. We need to understand what's happening in our whole interconnected planet. The first iteration of the data behind Global Forest Watch was actually done in 2013. And I'd argue this is perhaps the first cloud native geospatial project ever done, using one of the key cloud innovations, Google Earth Engine. Traditionally, geospatial has been done on desktop tools, but they're just not capable of processing data at the scale you can in the cloud. You can see from the quote, they did in several days what previously would have taken 15 years. So this type of global scale just hasn't been possible because of the amount of data you need to process. You need the cloud for it. Cloud native geospatial is also the only way to handle this geospatial data explosion we're in the midst of. These are graphs from a handful of Earth observation archives. The story is repeated everywhere and then multiplied with commercial data. And everyone understands there's this avalanche of data that's already started, and it's only going to accelerate with new space missions, higher bandwidth, and geospatial-enabled terrestrial sensors everywhere, in your cell phone, in your car, et cetera. And this explosion of data is just outpacing the growth of desktop hard drives. This was the largest one I could find in a couple minutes of searching on Amazon. And I was actually surprised that it's only 20 terabytes, and this is clearly a very big, beefy thing. And with that, this previous workflow of downloading data, even for analysis of smaller areas, starts to become intractable unless you're only going to use a small portion of the data gathered. So Cloud Native Geospatial also enables this shift to streaming, just like movies and music. People used to have copies of MP3s and movies on your computer. You'd collect the ones you'd like so you could watch them. And geospatial experts today still kind of collect their favorite data on their desktop, but we're starting to see this shift in Cloud Native Geospatial enables to a world where everyone has instant access to all the geospatial data in the world. Just like you can instantly stream any song or movie, you should be able to stream any geospatial data without having to keep that copy locally or wait for it to download. And this in turn reduces the amount of data duplication. This is a Landsat image after Hurricane Maria, and these kind of popular open images, they're just downloaded many times. I would guess hundreds, if not thousands, of times for desktop analysis, copied into hundreds of locations, on the cloud to work with a particular tool. And this is usually every band of the full area. It's not even targeted, so every one of those is like 700 megabytes of copied data. Cloud Native Geospatial also enables real-time analysis. I'll use a forestry example again. The first deforestation analyses were more retrospective, kind of understand what deforestation has been done. Newer systems aim to provide alerts, on new data. And these types of workflows must be fully automated to get the data out fast enough to actually do something about it, to stop deforestation that's happening instead of just assessing what has happened. And to do that, you need the workflows on the cloud. You'll likely need some machine learning, and that's a whole other talk. We need that cloud environment to just send the data straight out. And then finally, we aim to make data more accessible. Having that single canonical location for the web means geospatial is compatible with search engines. So this is a search term. This is a pretty contrived example, I will admit, but it kind of shows that potential. You should be able to search for imagery on Google and be able to see it and use it right away. Do the basics in the browser, zoom in high resolution, but just be able to enter a search term of planet disaster data from Hurricane Harvey. I want it with an open license. I want it from SkySat. And you can see as there's more and more of this online, these searches will get better as people link to them more and more. And the goal is to enable to spend most of their time actually analyzing the data instead of finding it. This article is about data science in general, but it's equally true in geospatial. And with Cloud Native Geospatial, we believe we can break out of this paradigm, make it finding the data needed for analysis as easy as a Google search. We also believe it will make geospatial more accessible to developers by fitting into their standard workflows and tools instead of being a kind of special geospatial tool that works in the way things did 5 or 10 years ago. It's data on the cloud, make use of it. And getting these foundations right will ultimately, we believe, make geospatial more accessible to all users. Geospatial has long been a pretty niche thing. You needed training, tools cost thousands of dollars, you needed to buy data. With Cloud Native Geospatial, we can help open real geospatial analysis to all. Obviously, it's a number of steps from just COG and STAC to making this data much more accessible, but I do believe these are kind of key building blocks. They'll become the foundation of geospatial being something that everyone can do. So now we'll shift to get into an update on the current state of Cloud Native Geospatial. So COG has really established itself as a core building block. It's a really nice state of maturity, and I think we're to mainstream adoption with many data sets are becoming available in COG and more coming online every day. I kind of can't even keep track of it, which is awesome. I learned about a whole lot of new COG data sets and finding content for this day. The list of tools that support it is very long. I think we even need to update this. It's becoming a format that pretty much must be supported. ArcGIS Pro, as I mentioned, now even supports reading and writing of COGs, and it's one of the formats that they do recommend. And then Earth Engine, so they produced COGs for a while, but they just recently brought in the ability to read COGs. I didn't have time to make the really cool demo that shows, you know, I'm not an Earth Engine expert, but you kind of any of that power of Earth Engine of different band visualizations and different operations you can do directly on the cloud optimized GeoTIFFs. You no longer have to import into Earth Engine, which is pretty amazing. And it's awesome to see the originator of Cloud Native Geospatial join in on the standards. You'll also see a lightning talk later on how they're embracing STAC. Yeah. Rio COGeo has emerged as the most capable tool for creating and validating COGs. And then GDAL now even supports COG as a first-class citizen. GDAL is really the first tool to support COGs, but now you don't have to remember the exact command, and it does it all more efficiently. Evan's going to give a talk about this. And then we're also already into this second generation of Lambda Google Functions style tilers. These scale infinitely, and T-Tiler is adding some really cool integrations with STAC, so you can render whole catalogs and search results. And Jeff and Vincent will share all about this in their intro session. COG's also become my favorite anthropomorphized file on Twitter. It's definitely worth a follow. There's lots of updates on great uses of COG, and occasionally it has tips with other file formats, which is interesting to see. As for what's next, COGs have really filled a great niche and have great uptake in software tools. So there's not a ton left to do. You know, we do want to see every relevant data set in COG on multiple clouds, you know, anything that's open and even everything from providers moving into COG. There's a bit of work to formalize the specification. It's been pretty informal and it works really well, but we've been discussing with OGC about them helping. They recently took over GeoTIFF and got that as a full release. So a COG extension makes a lot of sense, and we're in talks with them. And then there's a couple informal extensions that we would be good to standardize a bit more. A lot of tools support them, but we haven't kind of formally said, hey, this is what this should be, both a web optimized profile and then some stats to help visualization, especially of analytic data. We've also seen a couple new formats for cloud geospatial emerge. So beyond just COGs, the big area where COGs often fall short is raster data with a huge number of dimensions. So places where NetCDF, HDF have traditionally shined instead of TIFF, that's the sort of question of what's that cloud native equivalent of that. The cool thing is there's a couple emerging options. TileDB is a universal data engine, and it really excels at time series data. And they have this core cloud native format that works extremely well for geospatial. Norman will tell you about this in his lightning talk, and you can dive deeper in his intro session. And then ZAR has been emerging as a go-to format for climate scientists and others looking to go cloud native with NetCDF type data. Anderson's going to give a lightning talk on the format, and Amy will do a deeper intro session that goes into all the details. And then in her lightning talk, she also has some highlights of ZAR data as well. And then finally, STAC. So the biggest news is we released 1.0 beta. We're actually on beta 2. We did a couple little schema fixes. And to do this release, we split the specification into two parts. There's the core JSON fields of item, catalog, and collection. And that just went to 1.0 beta. And then the API is now its own repository. It made sense to split them as they kind of felt a bit different, and we wanted to be able to evolve them separately. The API depends on OGC Features API, formerly known as WFS3. And so we want to be able to kind of track and paste that. So the STAC API has a dependency on STAC Core and on Features API. And our goal is to really merge with that Features API and make STAC to be more of a best practice. So we hope to get the API to beta 1 soon. We want to align with OGC CQL and transaction extensions. We sort of did our own and yeah, bring it into OGC as a community standard once we reach 1.0. We continue to have a whole bunch of diverse contributors. 39 different people have contributed, and cool to see as people are contributing more. So there's up to 17 people that have had more than 10 contributions in the spec, and a whole lot more activity outside of that. So at this point, I'd normally do a quick survey of all the incredible tools and data in STAC, but the rest of the day is going to be a much better survey of all that stuff. So I'll just say there's a whole bunch. Check out the lightning talks, and you'll learn a whole lot more. And we're really sprinting together next few days to make this happen, to get more tools and more data sets in the next couple of days. There's one I did want to highlight because we didn't manage to get a speaker on it, and that's USGS and their adoption of STAC and COG for all of Landsat Collection 2. They're the first major government program to truly embrace STAC and COG, and have become early adopters, probably more so than they're usually comfortable in, but they really saw the huge potential of format. So all the Landsat data with the release of Collection 2 will be in STAC and COG. And then what's next? The big thing is achieving 1.0 for the core and the API, and that's the point of the sprint and the outreach day. There's really cool work just started in the past couple of weeks on indexing STAC, and that's sort of been our long-term goal, is have enough data out there that others start to index it. Matthias has up stackindex.org, and he'll talk on that later. And then Esri also used their geoportal to call STAC, and they'll share about that. And finally, I hope we can really get provenance tracking right. We have this opportunity where we're early in the cloud, the shift to the cloud. So let's kind of get that right, where you're able to track, hey, this data on STAC came from this one, came from this one, came from this one, and really kind of understand where data comes from. So yeah, getting these foundations right, we believe will make geospatial accessible. And yeah, I just wanted to share a couple words on future. So yeah, the big thing is maturity. I think we're really on the precipice of mainstream adoption, where it becomes the normal thing. COG, I think, is pretty much there, and STAC, once we get to 1.0, I think we're really going to see that take off. And the cool thing is these should stay as pretty stable layers, and then there'll be lots of innovation on top of those and more added while we keep a really stable core. I think two cool trends worth mentioning. I think we're at the time where there might be some sort of cloud native vector format that makes sense to emerge. Javi from Cardo will share some thoughts on this, and he's actually the one that inspired me on it. But looking at these data warehouses like Snowflake software, sort of BigQuery, Microsoft's, there's a kind of different way of operating that I think has a lot of potential, and we need to make it compatible. And it may just be it's data.json or a flavor of that, but I think we want to explore those workflows with vector more. And then the other one is full browser-based remote sensing. The EOX Cog Explorer showed some of this, but there's also been experiments with data tiles, and yeah, doing that full remote sense in the browser. We have a few different talks later today that will explore various aspects of it, but I think there's potentially another little standard there that helps make that available. So yeah, I think that's it. Looks like I did not leave time for questions, but I think the key time for questions is later today in the intro sessions. So join the intro sessions if you do have questions. I'll be doing one at the end of the day on kind of Q&A on all this stuff and an opportunity to dive deeper. So join that if you have burning questions and want to learn more.